seasons, we're talking about 4 distinct times during the year that the temperature, the humidity, and weather patterns all shift. New York State and other mid-latitude areas of Earth's northern hemisphere experience 4 seasons: winter, spring, summer, and fall. Seasons are distinguished by differences in temperature, moisture, and vegetation. What controls the seasons? Well, our previous video said, it's revolution. It's not revolution alone. So in this video, we have the Earth revolving around the sun. It is not to scale. The Earth looks just like the same size of the sun, and that's completely false. But this is meant to show that the path of the sun is the same in the summer, as shown here, and the sunlight angle in the summer, as shown here, is the same at all times as the Earth revolves around the sun. So there's never a change in the intensity of sunlight. It's never a change in the path of the sunlight in this model. Well, obviously we know that's not true. We know that summer's hot, we know winter's cold, we know fall and spring are kind of in the middle. So what's the difference? If it's not just revolution around the sun, what's the big driving force that controls our seasons? It turns out it's the tilt. Because the Earth is tilted, there's a time of the year where the northern hemisphere is facing the sun, which creates a longer path, shown here, and more intense sun rays, shown by those arrows, and then also a time during the year where the Earth is facing away, so the northern hemisphere then is not directed towards the sun, and that correlates with colder temperatures, lower sun angles, and a lower sun height in the sky. So ultimately, it's not revolution, and it's not a changing distance, it's the tilt. So the Earth is tilted at an angle of 23.5 degrees, and this is the primary reason why Earth has seasons. Let's just take a look at a slowed down version. So here's the sun and the Earth. In this position, the North Pole is facing the sun, and the South Pole is facing away. So in the northern hemisphere, we have our summer solstice. Revolve counterclockwise. In this position, after summer, we have our fall equinox. Difficult to see in this image, but you have to imagine that the sun and the Earth are in the same plane. So right now the sunlight's directed towards the equator, so both north and southern hemispheres are getting the same amount of sunlight. Only to revolve to this next position called the winter solstice, where now the southern hemisphere is pointed towards the sun and the northern hemisphere is pointed away. Because of that, this is our winter solstice. This is when we have our coldest time of the year. And then finally, the last position, our spring equinox. So let's talk about those terms, equinox and solstice. An equinox is a time when the sun is directly overhead at noon and directed towards the equator. And there are 12 hours of daylight and 12 hours of darkness all over Earth. So when I hear the word equinox, I think of equal day, equal night. And the 2 times during the year that happens, September 22nd and March 21st, marking the fall and spring equinox for the northern hemisphere. The other type of seasonal change is a solstice. And a solstice happens 2 times during the year. And that's when the rays of the sun fall the farthest from the equator. So the northern hemisphere summer solstice is when the sun rays are directed towards the northern latitude called the Tropic of Cancer. And during the southern hemisphere summer solstice, which is our winter, the sunlight rays are directed towards 23.5 degrees south, which is the Tropic of Capricorn. Sounds confusing? We will be practicing this a lot. So I'm going to focus right up here. Notice how these 5 arrows are now almost pointed towards the North Pole, right? That correlates, let me just pause it and rewind it. That correlates with our summer solstice. The North Pole, right up here, is pointed towards the sun. Well, if I look here, my sun rays are pointed and focused at northern latitudes. And if the Earth rotates in this picture, well, the northern hemisphere has more of an area in the light, and the southern hemisphere has more of an area in the dark. So to translate that into something that makes sense, there are more hours of light in the northern hemisphere during the summer, and there are more hours of darkness in the southern hemisphere during our summer. And if I look at this diagram, the arrows, the sun rays, are nearly perpendicular to the ground. The higher the sun angle, the more intense the sun. So I'm going to hit play again on the video to show you what happens on the opposite end. So here's our sun traveling to the equinox. Notice how the rays of sunlight are perpendicular to the equator. They're focused on the equator. There's even a little yellow dot over the equator in the picture on the left. And then when we're in our winter solstice, when we're in our winter position here, now we're looking at a lot of the opposite features that we saw in the summer. The rays of sunlight are directed towards the Tropic of Capricorn, which is the southern hemisphere. Okay. If I were to rotate the Earth, the northern hemisphere would have more hours of darkness versus the southern hemisphere having more hours of daylight. And the angle of sunlight for the observer, the stick figure, the rays of sunlight are almost horizontal. Not quite, but pretty close. The more horizontal the rays of sunlight, the more spread out the sunlight. And if I spread out my sunlight over a larger area, it's not going to make any one area warmer. So that has a really big effect on why it's colder in the summer, because the sunlight we're receiving is not at a very high angle. Okay, and then to finish this animation, getting us to our what would be our spring equinox, you can't see what's going on here because the back of the Earth is facing us, but over here you can. So during our spring equinox, the sunlight is directed towards the equator, and that's exactly what an equinox is. So some other diagrams that fit what we're talking about. Here's the summer solstice. Okay, sun rays are directed towards the Tropic of Cancer, which is our northern latitude of 23.5 degrees. If I were to rotate the Earth here, if you were above the Arctic Circle, which is 66.5 degrees north, you would experience 24 hours of daylight on this day. The sun would never set. If you were at the Antarctic Circle, 66.5 degrees south, if the Earth rotates, you would not have a sunrise at all. Okay, the sun would never rise above the horizon. You'd be in complete darkness for 24 hours on that day and every day up until the next season change. Okay, here's the winter solstice. Notice how our hemisphere, the North Pole, is pointed away from the sun rays, and now the sunlight is directed towards the Tropic of Capricorn, and as a result, the Tropic of Capricorn is where the most intense rays are. So this is the summertime if you live in the southern hemisphere, but it's wintertime for the northern hemisphere. And just like before, if I rotated the Earth, the North Pole would be in complete darkness and the South Pole would be in complete daylight. And finally, the two equinoxes. They look very similar because the sunlight is directed towards the equator. So equinox, equal day, equal night. Look at this line that cuts down the model. This black line separates daytime and nighttime. It cuts the Earth perfectly in half because the Earth is really divided in terms of equal day and equal night. So that's our first look at seasons. We will look at seasons over the next couple of days in much more detail by focusing on the path the sun takes for our latitude, the path that the sun takes for other latitudes, and in addition to that, how we can use the sun's path to determine what season we are in. Thanks for watching.